In this video, we will talk about compact sets. Some of the subtopics we will cover is open covers, subcover, of course the definition of a compact set and an alternative way of defining a compact set, as well as how to prove sets are compact or not compact, and then to the useful Heine-Borrel theorem, which gives you an alternate way of showing a set is compact, a couple of other theorems and corollaries. As we start to look at the definition of a compact set, we need to start with the definition of an open cover. If F is a family of open sets whose union contains a set S, then the family of open sets is called an open cover of S. So our example is if S is equal to the set 0, 1, which I have in black here, and it's the open set 0, 1, then F1, F2, and F3 are sets that when you union them together, S is contained in their union. So F1, F2, and F3 is an open cover. So let's just take a quick look at F1 is negative 1/2 to 1/2 over here. F2 is 1/2 to 1. So far it covers all of S except for possibly 1/2. But then we have F3, which is in green here, from 1/4 to 3/4. So now we've covered the entire set S. So F, being the union of F1, F2, F3, is an open cover for S because S is contained in the union of F1, F2, F3. And our notation for a family of sets, we usually have the script F, and here we have a script G for a family of sets, is equal to the F of alpha, where alpha is an index set. So in this example, alpha is equal to 1, 2, and 3 because those are the indices of our sets F1, F2, F3. So F is equal to F alpha, where alpha is equal to 1, 2, 3, 1, 2, and 3. Also, we have the notation S now is contained in the union. Alpha is equal to is in our set A, our index set, F of alpha. Next, we have the definition of a subcover. If G is a subset of F, and G is also an open cover of S, then G is called a subcover of S. So here I have my same example where I have S is equal to 0, 1. I have my F1, F2, and F3 as before, and then I just threw in another set, F4, which is at negative 3/4 to 1/4, so you can kind of imagine where it would be. Well, this set also, when I union the 4, they also contain S. So F1, F2, F3, and F4 is an open cover for S. But then we can look at our original. G1 is equal to 1/2 to 1/2. G2 is equal to 1/2 to 1, and G3 is equal to 1/4 to 3/4. So our negative 1/2 to 1/2, G2 1/2 to 1, and 1/4 to 3/4. But this set is a subset of F. This family of sets is a subset of F, but it covers S more efficiently than F, and it is called a subcover. We still haven't shown that S is compact. In fact, we'll see any open interval is not compact, so this is a good time for me to go over the definition of compact. A set is said to be compact if whenever it is contained in the union of a family F of open sets, it is contained in the union of some finite number of sets in F. Another way of saying this is S is compact if and only if every open cover of S contains a finite subcover. As I had mentioned, we haven't shown that the open set 0, 1 is compact, and in fact it is not. No open interval is compact, and that is because while it does have a finite subcover, to be compact it means every open cover of S has a finite subcover. We haven't shown that yet, but we will show that later. Two more examples of open covers. First, if we let S equal the open interval 0 to 2, so that's in black over here. And for each n in the natural numbers, we're going to let an, so this is a family of sets, equal 1 over n comma 3. So here, when n is equal to 1, we have the open interval from 1 to 3, that's A1. For A2, we have the open interval 1/2 to 3, so that's shown in green, 1/2 to 3. For A3, that would be 1/3, the open interval from 1/3 to 3, that's shown in yellow. So you can see as n gets large, we're getting closer and closer to 0 on this side of the open interval. Here's the outline of the proof that there is an open cover, that AN is an open cover for S. I will go in more detail of this proof in just a minute. But first, let's look at another example of an open cover. So if we consider the whole space R2, so the xy plane, we can consider a set of open disk of radius 2, centered at each point xy, where x and y are integers, as an open cover of R2. So in other words, here we'll just take a point 0, 0, and then we can have this open disk of radius 2. And then if we take the point 0, 1 in blue, we have a disk of radius 2. We can, and then we do this for every single integer point on this grid line. And here we have one for 1, 2, 3, 4, 4, 2. We have our disk of radius 2. And you can see if everywhere we have disks of radius 2, eventually we will cover all of R2. So this would be an open cover of R2. And just a quick note of what an open disk is. A circle, you know, is all the xy points, such that x squared plus y squared is equal to 2. So here in this diagram, that would be this circle that's dotted. But the open disk are the x squared plus y squared that is less than 2 squared. So the open disk would be everything here, not including the dotted line. So it's kind of the interior of the circle. And if it were the disk, then it would include the boundary. And if it's the open disk, sort of like an open integral, it does not include the boundary. And just to be clear, these disks and sets, they don't actually have to be nice circles. So here, if S is a set outlined in black, then we can have all these other open sets, F1, sort of a circle, F2 over here, F3 here, and as long as the union contains S, then we can say that these sets are an open cover of S. We're going to return back to this example where we have a family of open sets where AN is equal to the open interval 1 over n and 3. So remember, A1 was equal to the interval 1, 3, which is in blue. A2 is the open interval 1/2 to 3, which is in green. And then A3 is the open interval 1/3 to 3 in yellow. And then we noted as n gets large on the left-hand side of the open interval, we're getting closer and closer to 0. So what we want to prove is that this family of open sets is an open cover for S. And then the next question we want to ask, is S compact? And here I just have some quick notes about what the AN look like, and that this family of open sets is an open cover because S is contained in the union of my open cover. To show that this is an open cover, we need to show that every x in S, so every x in the open interval 0 to 2, is in one of the AN. And to do that, we will use the Archimedean principle. And for your reference, I have the Archimedean property here. For each real number z, there exists a natural number n such that n is greater than z. We're going to use this second property, or the equivalent property of the Archimedean principle, which is for each x, real number x, there exists a natural number n such that 1 over n is between 0 and x. So the next question, is S compact? Which is another way of asking, is there a finite subcover? Does F have a finite subcover? And the answer, it is not compact, and we're going to prove this using contradiction. So we're going to assume that we have G, a finite subcover. So it's AN1, AN2, up to ANK. and that's going to be a finite subfamily of F. In which case, there's going to be M is equal to my maximum N1 over here. So in this example, between A1, A2, A3, A10, A10 is going to be my maximum indice. So we're going to look at our maximum indice. So the union of my finite number of subsets, if M is equal to the maximum of all these indices here, then AM, the union is going to equal to AM, which is the open interval from 1M to 3. So G is not an open cover because if I look at 1 over M plus 1, it will not be contained in G. Therefore, we cannot have a finite subcover, and S, the interval 0 to 2, is not compact. And note, it's very easy to find an open cover that's finite. So for example, the open interval -1 to 3 is an open cover of 0, 2. However, to be compact, it's not enough to find a finite subcover. It's necessary to show every open cover has a finite subcover. And we just showed that the AN over here cover does not have a finite subcover, so S is not compact. Next, we will look at showing the open interval 0 to 1 is not compact. And in general, any open interval is not compact. To show something is not compact, we have to find an open cover that has no finite subcover. So we could go with the AN is equal to 1 over N1, very similar to the approach we did for the last example. But for this example, we're going to use this open cover, which is a set of nested open sets. So AN is equal to 1 over N, and then on the right-hand side, we have N minus 1 to N for N greater than or equal to 3. So we have A3 is equal to 1/3, 2/3, and that's in blue. A4 would be equal to 1/4, 3/4, which is in green. And A5 is equal to 1/5, 4/5, which is in yellow. So you can see these, each subset is nested inside the next set. So the claim is that this set of AN is an open cover for 0, 1. And to formally show it is an open cover, we need to show that for any element x in our S, in the interval 0, 1, that x is in some AN. By the Archimedean principle, for any real number x, there exists a j and k in the natural numbers such that 1 over j is less than x, and x is less than 1 minus 1 over k. So for example, if x is equal to 1/5, then j can equal to k, which is 6, because x is less than 1/6, and x is greater than 1/6, and x is less than 1 minus 1/6, which is 5/6. For x equals 2/3, then j equals 1/3, and x is greater than 1/3. We can't set k equal to 1/3 because that would be 1 minus 1/3, which is 2/3. So x is not strictly less than 1/3, but we could say k is equal to 4, and then we get x is less than 3/4. So then what we do is we let n equal the max of j and k, and we set our AN equal to 1 over n minus 1 n. So in this case, our max is k, and it's always k is going to be greater than j. So our x is going to be between 1/4 and 3/4. So this is how we come up with a to the n, just looking at 1 minus 1 over k, that's the same as k minus 1 over k. So here we have our a to the n. So we've shown that this set covers 0, 1. However, no finite number of a sub n will cover 0, 1, and we'll prove that on the next slide. And no finite cover will cover 0, 1 because if there is a finite subcover, then there's a max n. But 1 over n is not contained in A3 union up to AN. For example, 1/5 is not in 1/5, 5/4 because this is the open interval. So no finite subcover will cover the interval. Our next example is to show any finite set is compact. We will start by letting S equal a representative finite set, so it has elements x1, x2, up to xn. And then we're going to let F be a family of sets that's an open cover for S, so possibly infinite. So F is equal to F1, is equal to A1, A2, up to possibly infinity. And here is a super diagram of our S. Since F is a cover, we know that each element x sub I is an at least one a sub n, and I used n because I didn't want the same subscript as my x sub i's. So for example, x1 might be an a2, but it's in some a sub I. x2 might be an a sub j, maybe it's a3. x3 is an a sub m, maybe that's a1. But the idea is that each of these elements has to be in at least one of these sets, since the sets cover. And it could be that it's in multiple of the a sub n, but it's in at least one. Here I have my picture showing that x1 is in a2 as well as a1. And for example, x4 is in a3. Well, since each x sub I is in at least one set of the sets A, that means there's a finite number of A needed to cover S. So you just choose one A sub n for each element, and that will be your finite cover. And here I have this written out. So we have x is equal to x1 up to xn. It's a finite subset of R. We have our family, which is an open cover, family of sets. And for each I from 1 to n, there's a set A sub ai from F that contains x sub I, since F is an open cover. So it follows that if we choose one of the A sub i's for each of the x's, then we can have a finite, we only need n of them, and that should also cover S, and it's a finite set. So that means that any finite set is compact, since we can always find a finite cover. So what we've seen from our examples, if we want to prove a set is not compact, we have to find an open cover that has no finite subcover. It's more difficult to prove a set is compact because you must show that any open cover has a finite subcover. It's not sufficient to pick a particular open cover and extract a finite subcover. The times that we use the definition like this of an open cover and compact set might be if we have two sets that are, and we're trying two sets within that are compact and we're trying to union them or something. But in general, it can be difficult. We have this next theorem that gives us other conditions for determining if a set is compact and is quite useful to prove a set is compact. So here is the Heine-Borrel theorem. A subset S of R is compact if and only if S is closed and bounded. We will go through this entire proof, but before we do that, I did want to point out that one thing that's interesting about this proof is you use two open covers. This is an example of an open cover for the entire real number line. This is an example of an open cover for the real number line minus a single point P. Both of these are nested open covers, and what that means is the sets are based on n, so in goes from negative n to n, and the in plus 1 set will contain all of the previous in's. Similarly for un. I'll talk a little bit about these open covers and then we'll go through the proof. Our first open cover is for S, a subset of R, and we're going to denote it with in, which is the neighborhood of 0 with a radius n. So in other words, it's the open interval from negative n to n. So when n is equal to 1, we get I1, which is the neighborhood from negative 1 to 1, the open interval. For I2, that's the open interval from negative 2 to 2. And I3 will get negative 3 to 3. And you can see as n goes through all the positive integers, we're going to span the entire real number line. The next open cover we are going to look at is for the real number line minus a single point p. And the open cover we're going to use is un is equal to the real number line minus p minus 1 over n up to p plus 1 over n. I want to take a look at how this works. So I'm going to use, for an example, p equals 2. That's the number that's going to be excluded from my open cover. So if I calculate u1, so I'm going to have n equals 1. Again, p is equal to 2. So u1 is going to be r minus, and then this closed interval here. And the closed interval is going to be 2 minus 1 over n is equal to 1. So that's going to be 1. And then over here, the other point on the interval is going to be 2 plus 1 over 1. So that will be 3. So I'm going to exclude the real number line, everything between 1 and 3. So that's going to be my negative infinity to 1, union my 3 to infinity. So this is u1. u2 now, p is equal to 2, n is equal to 2. So that's going to be 2 minus 1 over 2, and 2 plus 1 over 2. So that's going to be the interval 3/2 to 5/2. That's what's going to be excluded. So it's going to be the real numbers up to 3/2, union 5/2 up to infinity. So this is what it looks like. And you can see as you increase n, u3, you'll get closer and closer to 2, but you'll never quite reach 2 because essentially, right here you have 2, and as n gets very large, this gets very small. So you're getting close to 2 on this side, and again, as n gets very large, this gets very small. So you're getting closer to 2 on this side. So this is how you would do an open cover for everything on the real line minus this point p. And for our proof, since it's an if and only if, we have two directions to prove. So we'll prove the forward direction first, which is that a set S is compact implies it is closed and bounded. And to prove this, we're going to find an open cover and then use its subcover to show that it is closed and bounded. The open cover we used is the one we had discussed previously, where IN is the neighborhood centered at 0 with radius n, or the open interval negative n to n. And we talked about how this would be an open cover for S, a subset of the real numbers. Since S is compact, IN will contain a finite subcover, so we can label that S is contained in some subset, IN1, IN2, up to INK. We see that our INK is equal to IM, where M is the maximum of N1, N2 up to NK. So in other words, because they're nested, IM will cover the set. So because it is compact, we know that any element x is less than m, the absolute value is less than m, and for all x in S, in this subset of real numbers, x is bounded because the absolute value is less than m. To show that S is closed, we're going to do that by contradiction. We're going to assume S is not closed. And remember, S is closed means that S is equal to the closure of S. The closure of S is equal to S plus its accumulation points. Another way of looking at that is S plus its boundary points. So that must mean we have something out that's an accumulation point and not an S. So in other words, we have some point P that keeps it from being closed. So that point P is in the closure of S, but is not in S. For our proof, we're going to build an open cover, and we're going to use this open cover UN we had discussed before, which is for the real numbers, excluding a single number P. And again, we said as n gets large, and in the natural numbers gets large, these fractions, the 1 over n, get smaller and smaller. So we basically narrow down to the single point P. That is our relative complement, that single point. So that's going to be our open cover. You can see each UN is an open set, and as each UN gets closer to 2 but never reaches 2, you can see that the UN is equal to the real numbers minus P, and that is a subset of S. So you can see that UN is an open cover for S. Since S is compact from our starting hypothesis or assumption, then that means there must be a finite set of UN that also covers S. In other words, S has a finite covering set. Furthermore, the UNs are nested. You could see that in the previous slides. So that means that S must be a subset of U and K, where the U and K is our biggest outermost subset. But now, because there's a finite number of U and K, you can't get arbitrarily close to the point P, or in this case, in this example, the point 2, because each U and K gets a little bit closer to 2 as you're closing in, but there's a limited number of them. So you can only close in so far, and at some point, you're going to have a neighborhood of P with radius 1 over nk, where S intersect that neighborhood is equal to the empty set. And you can see that radius is 1 over nk because that's how we constructed our UN. But now this intersection being empty contradicts the fact that P is in the closure of S minus S. But the closure of S means P is either in S, in which case this intersection would have to be non-empty, or P is in the, it's an accumulation point, in which case it would, any neighborhood of P has to have an intersection with S. So again, this line here contradicts that P is in the closure of S, and therefore our assumption here that S is not closed must be incorrect and S must be closed. For the opposite direction, we want to show that closed and bounded implies compact. So for an example, just to see what's going on, I have S is the closed set 1, 4. It's also bounded, and I drew it here on the number line. And we're going to let F be an open cover of S. So we're going to draw an open cover. And for every x in the real numbers, we're going to let Sx equal S intersect negative infinity to x. So what that means is we're going to have all these sets going from negative infinity up to some intersection with x. So we have this one that intersects with 1, and then we have another set that goes from negative infinity to intersect with whatever is over here. And there's, you know, an infinite number of them between here and here that goes from negative infinity to a real number x. So then we're going to let B equal to x such that Sx is covered by a finite subcover of S. So even though we have an infinite number here, we actually only need the one that goes from negative infinity and covers 4, right? Because that would be a finite subcover of F. And then we can throw in some other ones as well because it would still be finite. Since S is closed and bounded by this lemma here, and also it's something that kind of makes intuitive sense, if it's closed and bounded, then the lemma says S has a minimum, and we'll call that minimum D. Now if we look at Sx with respect to D, so Sd, that's S intersect negative infinity to D, and since D is the minimum, it's only going to contain the element D. So this is the start of our set B, so we know it's not empty because it contains at least the element D. And we also know that this Sd is covered by a finite subcover of F. So we have B is not empty, but because we want to show that S is compact, we need to find a subcover, a finite subcover. So we want B to be a finite subcover of F, and so we're going to start out by assuming that B is not bounded above. And by assuming it's not bounded above, it means we'll always be able to find a number z greater than sup s. So in this example, sup s is equal to 2. So in other words, we just need B to be able to have some number greater than 2. And if you recall, then sz will pick out the part of s that is less than z. But if z is the sup of s, then s of z will contain all of z. And since z is part of this B, we can conclude that there's a finite subcover and S is compact. So we're going to show that B is not bounded by contradiction by starting with assuming that B is bounded above, and we're going to let M equal the max or the sup of B. We'll have two cases where M is in S and where M is not in S, and both will lead to contradictions. Here we are with B bounded, and then because it's bounded, it has an upper bound, and we're going to let M equal the least upper bound. In other words, M is going to be the sup of B. And we're working on the case M is in S, and next we'll do the M is not in S, but for now we're looking at M is in S. Well, since F is an open cover of S here, then there exists some, and we're just going to call it F sigma, that such that M is in the set F sigma. And if M is in this set, then since F is open, that means there's some neighborhood completely of M completely in F. In other words, we're going to have an x1, x2 in F such that x1, that M is greater than x1 and less than x2. So M is between these two numbers. I have my drawing here. Here's S, and here's my value M. I have a set that M is contained in, and I have my x1 and x2, which M is between those two values. Since x1 is less than M, remember by our definition of Sx, those are the intersection of S up to with the greatest value of x. So that means there's going to be an open cover that cover Sx1 because that covers everything of the intersection with S with the greatest value of x1. But then we also have this open cover for Sx2 because, well, they're both in F naught here, which would imply that x2 is in B. But this contradicts, because x2 is greater than M, this contradicts the fact that M is the sup of B, and therefore our assumption here, B is bounded, must be incorrect. So I have that kind of shortened out and written here, but we also need to cover the case M is not in S. Next we have if M is not in S. So since S is closed, this is what S looks like. Let's just say we have S here, and then there's a break where we have M. But S is closed, so that means M can be isolated. There's some neighborhood around M that does not intersect S. So here there's some epsilon around M such that this neighborhood around M intersect with S is equal to the null set. So there's some neighborhood we can draw around M, no intersection with S. Then if we look at these Sm minus epsilon and Sm plus epsilon over 2, again looking at our definition here, over here, so Sm minus epsilon, so M minus epsilon will get us to the very border of S and M, is S intersect negative infinity including M minus epsilon. So that'll just get us the point including M minus epsilon, because M minus epsilon is not in this, that's the very boundary. Then, so S intersect with this boundary here, or negative infinity up to that boundary, is just this portion of S. If we compare that to Sm plus epsilon over 2, so that's halfway, but if we look from negative infinity up to M plus epsilon over 2, the intersection with S is the same as Sm minus epsilon. It's just this portion of S. So we have M plus epsilon over 2 is one of these B's, which contradicts our assumption that M is equal to the sup of B. So what we have is B is not bounded by above, and S is compact. Next, we have a couple of theorems and a corollary. First, the Bolzano-Weierstrass Theorem. If a bounded subset S of R contains infinitely many points, then there exists at least one point in R that is an accumulation point. The next theorem, if we have a family of compact sets of R, so possibly infinite, but it's a family of compact sets, suppose that the intersection of any finite subfamily is non-empty, then the intersection of the entire family is not equal to the empty set either. And then last, nested intervals theorem. We've seen a lot of nested intervals like this one up here, which was that an is equal to 1n over 3. Remember, these were nested. So if we have a family of closed bounded intervals in R such that an1 is a subset of an for all n in the natural numbers, then the intersection of all the an is equal to the null set. And here this is a little bit different, even though I kind of compared it, because these are open sets, and here it's a family of closed bounded intervals, so that's why you can get the null set here. And that's it for the main points of compact sets. Here are some 3 review problems for you to try, so you can pause the video, give them a try, and their solutions on the next slide. Here are the 3 solutions. And that is it for this video. Thank you for watching.